Today I'm going to prove that any particle under the influence of a center-seeking force will traverse an equal area in equal intervals of time with respect to that center. Here's what I mean. Let's say a particle is moving in this type of fancy direction. And let's say if the particle is here, there's going to be a force directed on it pointing that way. If the particle is here, there will be a force directed going outward. Or if the particle is here, there will be a force directed that way. But no matter what, the direction of the force is always aligned with the center. That's what I mean by a center-seeking force, or it could be a centrifugal force if it's pushing outward. And let's also say that the particle starts here, and it takes 2 seconds for it to get there. 2 seconds. And likewise, let's say the particle is here, and it also takes 2 seconds from it to get from here to here, or here to there. My argument is that these two areas are the same, if and only if it's a center-seeking force. And here's the proof. So basically, if it's a center-seeking force, the area swept out with respect to the center. If like the particle takes 2 seconds to get from here to here and from here to here, then these areas are the same, if and only if there's a center-seeking force. So let's take scenario 1, where a center-seeking force, or just center force, equals 0. In this scenario, we just have a particle moving in a straight line because the net force on it is 0. Hence, it won't change direction or speed up or slow down. And let's draw a Cartesian coordinate plane here with a center centered at the origin. And let's denote this height distance from here to here, h. All right. Now, let's say it takes a time t for the particle to get from here to here. So it takes a time t. Draw this. And by the way, the velocity is constant because the net force on it is 0. And let's say it takes the same exact time t for the particle to get from here to here. Now, I'm asking, are these two areas the same? And by the way, this isn't colored in. Are these two areas the same? So it takes a time t. These t are exactly the same. It takes a time t for the particle to get from here to here. It takes a time t for the particle to get from here to here. Are these areas the same? Well, let's find out. The area of a triangle is 1/2 base times height. So what's the base of this triangle right here? Well, the base of this triangle right here would just be v times t. So 1/2 base, or v times t. What's the height? Well, it's just h. And what's the area of the triangle on the left? Well, it's also going to have the base of v times t because velocity and time are constant. And it's also going to have a height h because it doesn't change directions. So we have proof that if the center-seeking force equals 0, then the area is conserved in equal intervals of time. And it's also the case if it's like, let's say, here to here. So let's say, remove that v here. Let's say it takes a time t for the particle to get from here to here. Well, this triangle right here will also have a base of v times t, and it will also have a height of h. So if the center-seeking force equals 0, we know that the area is conserved, or in equal amount of time. All right. Now, what if the center-seeking force is a non-zero value? Let me draw the origin, Cartesian coordinate plane. Let's just assume that initially there's a particle moving with a constant velocity, v0, but all of a sudden it gets struck by a rock or something, and it goes in this direction. But remember, the main stipulation I made is that the force, or the thing that's struck by, or has to be pointed towards the center. So, like this. Has to be pointed that way. And instead of thinking the force in terms of acceleration and force, well, we can think of it in terms of momentum. So we can just say this is velocity applied. And finally, it ends off with the final velocity of velocity final. All right. Now, let's split these velocities into their components. So the component of this velocity right here would be negative v naught, 0. 0 because it's not moving in the y direction, negative because it's moving in the negative x direction. And likewise, if we denote this as theta, the components of VA here would be positive VA cos theta because it's directed to the right, and negative VA sin theta because it's directed downwards. And finally, VF will just be the sum of these two vectors. So this would be VA cos theta minus V naught and negative VA sin theta. All right, now it may seem random at first, but let's just call this height here from here to here h naught, and let's find the area of this triangle. And also let's make a line here that is perpendicular to the velocity line, but also touches the center. Yeah, like this may seem random at first, but this is pivotal to my argument. So like I said, we want to find the area of this triangle. Well, what's the area of this triangle? Well, the first way to find the area of the triangle is to use this as a base and use this as the height. Now, let's call this this height right here h final. So this slope right here would be h final, and then what's the length of this line right here? Well, let's just say after a time t, the particle gets from here to here. So that means this length right here would be, well, vf times t. If it takes the time t for the particle to get from here to here. Hence, the area of this triangle right here would be 1/2 the base vf times t times hf. But this triangle right here the area of this triangle right here can also be written differently. We can treat this as the base and this as the height. But luckily we already know what the height is. So let's split this base into two parts, this part and that part. Well, what's the distance? What's the length here? Well, the length of this is just the x component times the time. You can prove this using Pythagoras' theorem with the right triangle a squared plus b squared equals c squared. So this length from here to here would be v naught minus va cos theta times t. And this t is exactly the same as that t. You can prove this using Pythagoras' theorem. The reason why I switched the v naught around with the va cos theta is because this gives me a negative velocity value, but I want a positive length value. So if you flip these two terms, it goes from negative to positive, but the magnitude stays the same. All right. Likewise, what's the length of this to this? Well, this is just the x component of VA. So this length right here from here to here would have to be VA cos theta times time. And this length right here from here to here would be VA times t. And likewise, h naught would equal VF times t, or no, it would just be VA sin theta times t. The reason why t appears everywhere is you can prove this using Pythagoras' theorem. All right, just know that, all right? So if this length right here from here to here is VA cos theta times t, and this is V naught minus VA cos theta times t, we sum these two together to get the base. So 1/2 V naught minus VA cos theta times t plus VA cos theta times t. And the height is just h naught. Now, let's simplify our expression here. So 1/2 VF HF times time equals 1/2, well, negative VA cos theta times t. If we distribute the t to V naught in that term, just cancels out with this. So we end up getting just the V naught here times t. times h naught, and hence 1/2 VF HF times time equals 1/2 V naught H naught times time. We can further simplify this too if we divide both sides by 1/2 in time. VF HF equals V naught H naught, or that the product of V naught times H naught equals the product of HF times VF. Now, this is very important. Let me go to another page. So, let me redraw it again. So it's moving with speed of V naught, VF, and the height of this would be HF, and this would be H naught, and V naught H naught equals VF HF. So let's say it takes a time t for a particle to get from here to here. And let's say similarly, it takes a time t for the particle to get from here to here. Exactly, these t's are exactly the same, but these velocities may be different. Are the areas of these two triangles the same? Well, we can find that out. What's the area of this triangle right here? Well, it's just V naught times t is the base, so 1/2 V naught times t, and H naught is the height. And likewise, the area of this triangle would be, well, HF is the height, V final times t is the, if we just, flip it around, HF is the height, VF times t is the base. Remember, this line is directly perpendicular to this line. So we get that the area of this second triangle on the left here would be VF times t times HF. But as we said before, VF HF just equals V naught H naught. So this just simplifies this down to 1/2, well, V naught t times H naught, which is exactly the same as the area of this triangle. And I'll give you one more example, because I've already proven that it doesn't matter whatever motion it is. It just has to be a center-seeking force. The force has to be aligned with the center, and the area is always conserved. That's what I proved. This not only works for ellipses, but also works for this type of, abrupt motion too, if and only if the force is directed to the center. So let's take this motion right here, and the particle goes here. So let's say it takes a time t, and this is the center, and let's say these abrupt changes in direction are caused by a center-seeking force. So let's say it takes a time t for the particle to get from here to here, and a time t for the particle to get from here to there. And let's say initially you have a speed of v naught, then it has a speed of v1, then it has a speed of v2, then it has a speed of v3. And likewise, it initially has a perpendicular height of h naught, perpendicular height of h1, h2, and h3. We know that v naught h naught equals v1 h1 equal v2 h2 equal v3 h3, because as I proved before, if it's a center-seeking force, these values will have to be the same, and h is the line that is perpendicular to the direction of motion. So what would the area of this, or this set of two triangles be? So let's split it up into two triangles, and let's say it takes a time t1 for it to go from here to here, and a time t2 for the particle to go from here to here, and t1 plus t2 equal t, because they need to sum up with t, because as we stated before, it takes a t for it to do the full motion from here to here. Then the area of this weird looking shape here is just the area of two triangles. So the area of this triangle would be 1/2 base, so this would be v naught times h naught, or v naught times t, and then t1 times t1 times h naught. That's the area of this first triangle right here. And the second triangle would have an area of 1/2 v1 times t times h1. And like we said before, v naught h naught equals v1 h1. So this thing right here just simplifies down to 1/2 v naught h naught. If we factor out 1/2 v naught h naught, t1 plus t2. Oh, this is t2 by the way. And as we said before, t1 times t2 is just t equals 1/2 v naught h naught t. What about from here to here? Likewise, we can just say this time right here, if it goes from here to here, it's t3. This, and when it goes from here to here, it's t4. And t3 plus t4 also equals t, because we said that the time it goes takes from it to go from here to here is t. So what would the area of these two triangles be? Let's draw a triangle here, or split it up into two triangles. The first triangle right here would have an area of 1/2 v2 times t times h2. And the second triangle would have an area of 1/2 t3, 1/2 v3 times t4 times h3. And like we said before, that v2h2 also equals v naught h naught, and v3h3 also equals v naught h naught. So this just simplifies down to one-half v naught h naught times t3 plus t4, which, as we said before, t3 plus t4 must equal t, so 1/2 v naught h naught t. And hence, these two areas are the same. And you can also think of this for a constant force, like not abrupt, but let's say something's moving in a type of circle, or that type of motion. The area must be conserved, because you can just use my method here and just split it up into many triangles, and your end result is always the same. So yeah, that's the proof, and I hope you enjoyed the video. Bye.